We will consider this problem from the Moscow Mathematical Olympiad. The numerator has one more square root than the denominator, and the question is to prove that the quotient is greater than 1 over 4. Alright, so here is the problem. We want to prove that the quotient where the numerator has one more square root and the denominator is greater than 1 over 4. Alright, so the first thing that we will do is we will introduce this notation, an. We have n terms here, which is the same as n square roots. So for example, if n is equal to 1, a1, it will have a single square root, so it will be square root 2. When n is equal to 2, we will have 2 square roots, so a2 will be the square root of 2 plus square root 2, etc. Alright, so now if we actually plug in this an and an minus 1 in the inequality right here, the question becomes to show that this inequality holds true. The numerator has one more square root than the denominator, so therefore we will have an extra square root, so the numerator will be an here, and in the denominator we will have an minus 1. So then our original inequality can be rewritten as 2 minus an over 2 minus an minus 1 greater than 1 over 4. Alright, so the next observation is to get a recursion between an and an minus 1. Alright, so an has n square roots, and after the square root we will have n minus 1 square root, so this expression right here will be an minus 1. So therefore an is equal to the square root of 2 plus an minus 1. And this gives a recursion between an and an minus 1. Alright, so a1 is the square root of 2. It will be less than 2, clearly. And a2, by the previous recursion formula, it's the square root of 2 plus a1. And since a1 is less than 2, this whole thing will be less than square root of 2 plus 2. Again, that's because a1 is less than 2. That's the square root of 4, which is equal to 2. And in the general case, if the previous term, an minus 1, is less than 2, then the next term, an, which is the square root of 2 plus an minus 1, this will be less than 2 plus 2 again under the square root. The reason is because of this hypothesis, an minus 1 is less than 2. So that's again the square root of 4, which is equal to 2. Alright, so each term being less than 2 implies that the next term is less than 2. Since a1 is less than 2, and actually a2 is less than 2, all the next terms will be less than 2, so therefore an will be less than 2 for all n. Now, since an is less than 2, the denominator right here is positive, so therefore we can just cross multiply here, and since the denominator is positive, it will not change the direction of this inequality. So when we cross multiply, we will get 8 minus 4 an, which is right here, 8 minus 4 an, greater than 2 minus an minus 1, which is right here, 2 minus an minus 1. And if we just move everything to the left-hand side, well, not everything, just 2 to the left-hand side, and we move this 4an to the right-hand side, we will see that the inequality that we want to prove, so this is the inequality that we want to prove, it's actually equivalent to this inequality. So therefore it suffices to prove that 6 is greater than 4an minus an minus 1. Alright, so we go back to the recursion formula. An is the square root of 2 plus an minus 1. We will square both sides. So here we will get an square. And then after we square the both sides, I will subtract 4an from both sides. And I will also add 4 to both sides. The reason is because I want to get a complete square on the left-hand side. So an is squared, and an squared is equal to 2 plus an minus 1. And then we subtract 4an from both sides and add 4 to both sides. The left-hand side now becomes a complete square. An minus 2 squared is equal to 6 minus 4an plus an minus 1. And since this is a complete square, since this is a square, this has to be greater or equal than 0, but in our case it will be strictly greater than 0 because an is strictly less than 2, right? So an minus 2 squared will be strictly greater than 0, so therefore the right-hand side is strictly greater than 0, which gives 6 is strictly greater than 4an minus 1, and that's exactly what we wanted to prove because that's equivalent to the inequality that we want to prove. And that completes the solution. Thank you for watching.